All right, folks. Well, welcome back for round two. I know I wish we could avoid doing this, but I feel like we have to try to get the material in, and this is really important stuff. I think not only for the AP exam. I've seen a few questions asked about this here, but I think also for your understanding of how interactions work and the way that we can explain, connect macroscopic events to microscopic explanations. So the macroscopic observations that we can make here about magnetism, about bond energies, about the photoelectric effect, photoelectron spectroscopy, which we'll go over in just a moment. And the link between, and I'm hoping that you're able to make the link between experimental data, which we can collect, and the theory and the ideas that we can come up with to explain that experimental data is absolutely important. And it's central to good science. And so I think in this day and age, and I don't want to go on too long about this, but with everything going on here, I think the need for good science, and I think the need for accurate and provable science is absolutely important. Okay, and so with that said, then we were able to take a look at these electron configurations. So we came up with electron configurations for the nonmetals in period two here. And we see then that for the nonmetals in period two here, there are two possibilities in which the electrons can be arranged for the diatomic molecules of these period two elements. Okay? And so with that said, then there is a reason why, and there is an explanation that we can give for why boron, carbon, and nitrogen, diboron, dicarbon, dinitrogen, situate the electrons in this manner here, where we have the sigma 2p orbital being higher in energy than the pi 2p orbitals, and then it reverts back to what we predicted when we first came up with these orbitals. You have the sigma 2p, lower in energy at the pi 2p. The proposal here is that there is when S and P orbitals, S and P atomic orbitals get together to make these molecular orbitals here, that the importance of that, the mixing between the 2s and 2p orbitals decreases as you get across here. So that means then that mixing then will determine then the energy levels of these sigma and pi molecular orbitals. And as that 2s, 2p mixing becomes a little bit less important, you get a reversion back here to what we predicted. That's a little bit more advanced than what you need to know. I think what we need to know is we need to be able to come up with these electron configurations here, come up with them, and be able to support these electron configurations with data that we can collect about the magnetism, about the bond energy and the bond length here, and also using photoelectron spectroscopy, which is what I'm hoping to get to in just a moment. Okay. All right, so with that said, then hopefully I just want to point out one last thing for you here, and you notice here that the bond energies here that are related to the molecular orbitals, the bringing together the molecular orbitals, correspond, and the bond lengths here corresponds to the energies and the lengths associated with single, double, and triple bonds. Now again, these are not single, double, and triple bonds. Remember, single bonds, double bonds, triple bonds correspond then to the localized electron model, where those pairs of electrons stay between the two atoms. Here, what we're saying is the bond energy is the energy needed to break the interaction between these two atoms here, between these two atoms and so forth. Okay, and if you notice here, we see the same trend though, same trend occurring here, whereas the bond energy increases, the bond length will decrease, and that's what we saw with the localized electron model. So that as we go from, say, single bond here, if this were a single bond, it would have the lowest energy, but it would have the greatest bond length. Okay? So that also corresponds there. But here, what you also notice then is, if I can draw your attention to that, is that you notice here that the bond order. Remember, we calculated for the bond order, and we said then as the bond order increases, the strength of the bond also increases, and that's what we have here. How do we know that the strength of the bond increases? The energy needed to break the bonds also increase. So this bond order here that we calculated for, again, remember when we calculated for the bond order, that corresponded to the strength of the bond itself, and the stronger the bond, the more likely those molecules can exist here. And so what we're able to do here is we're able to compare the bond order for the diboron, dicarbon, and dinitrogen. And then if we were to use the localized electron model, remember, dinitrogen is held together by a triple bond, and that's why this interaction is very strong. So hopefully by the end of this chapter, end of this discussion, where I'm going to try to tie together both the localized electron model and the molecular orbital theory, what we've come to at this point in bond theory and theory at this point in time in bond theory is that the actual the explanation that is accepted then is a combination of both molecular orbitals and localized electron models. So both of those models are used together in order to explain then how atoms interact to form these bonds. Okay? All right. So that's what we have here. That's a summation of the bonds that we of the interactions that we have here. Hopefully you can use this table. I think is in your book. I forgot what page it's on. Please make sure you take a look at it and make sure you can understand the connection between the again, this is going to be the macroscopic, and let me go ahead and just quickly point that out. This is the macroscopic here. Okay, okay. This is what is observable. So this is the macro, and so we can observe this. This is observable. Okay, and this here is the microscopic, and that's not observable. That's the explanation. That's how we explain. Okay, these observable events here, so that we're trying to tie together the macro and the micro, and this is the explanation, and this we cannot observe, can't observe, but actually it is what we believe is happening at the electron level. Okay, all right, very good. So let's go ahead then. Let's go ahead then and let me save that really quickly, and let me ask you to do a couple here. Okay, let's take a look at number 7 in your problem set really quickly. Okay, I have laid out for you here oxygen. Okay, so this is the electron configuration for oxygen. Okay, so this is O2 right here, and when hopefully you recognize from the previous slide here, O2 here, where you have 2 electrons in the sigma 2s, 2 electrons in antibody sigma 2s star, 2 electrons in the 2 sigma 2p, 4 electrons in the pi 2p, and then 2 unpaired electrons in the pi 2p star. Okay, and so with that said, then the question then is, well, let's go ahead and do the bond energies really quickly for oxygen here. So bond energy, then remember when we calculate for the bond energy here, it's going to be equal to, and I'll write it down here, the bonding electrons minus the anti-bonding electrons. So we have 2, 4, 6, 8. Okay, so we have 8 bonding electrons. We have 2, 3, 4 non-bonding electrons. We divide that by 2, then we get the bond order of 2, which is what we got in the previous example. Okay, so so that we got that. Okay, the question then is, if this is the bond order of 2, okay, so keep that in mind. So make sure you write that down. Okay, what I would like you to do real quickly then is, I want you to use the table here. So let me go ahead and clear this out for you. Okay, use the table. Okay, and go ahead and write out the electron configuration for these 2 ions of the molecule O2. So the O2 cation and O2 anion. And hopefully you recognize the difference then with the O2 cation here is you have 1 less electron than the neutral form here, and the O2 anion, you have 1 more electron than the neutral molecule here. And essentially this is all hypothetical. We want to be able to use this to determine then bond strength and also bond order. Okay, go ahead and work this one out really quickly, and let's see what you come up with. Okay. Okay, let's go ahead then and let's write out these electron configurations for O2 plus. Okay, so let's take a look at O2 plus. Now remember, we have to account for the total number of electrons in each one of these here. So if in O2 we had 12 total electrons we have to account for. Okay, 12 total electrons that we have to account for. Hopefully you recognize then that in O2 plus, we have to account for 11 total electrons. Okay, so let's start filling. So I'm going to leave out the electrons on the atomic orbital side here and get you to see then that at some point, and I pointed this out to you this morning, at some point you have to be able to get the electron configuration without having to use this table. But the filling of the table is very similar to what we did with atomic orbitals in the way that you memorized how to write out the atomic electron configuration, the way that you remembered the way that you were able to write out the electron configuration for the atoms without using any tables, you have to be able to do the same thing here. So with that said, then 2 electrons in the first energy level. Let's go ahead and do that. 1, 2. That accounts for 2 of the 11, so they get 9 more. Okay, 1, 2, 1, 2. So that's 2, 4, 6, 7. Yeah, I said 2, 4, 6. And I'm sorry, 7, 8, and then 9. Okay. Did I count already? 2, 4, 6, 8, 9. Sorry, 2, 4, 6, 8, 10, and 11. Okay, 2, 4, 6, 8, 10, 11. Okay, so we got 2, 4, 6, 8, 10. Okay, so there we have it. Okay, so there is the electron configuration. So, so let's go ahead and write out the electron configuration for O2 plus. Then it's going to be sigma 2s with 2 sigma 2s star with 2 sigma 2p 2 pi 2p 2, and then oops, got a parenthesis in here, pi 2p star 1. Okay, so that's the electron configuration for O2 plus. And I'm let me clean this up for you a little bit, but hopefully you can see this here. Okay, go ahead and write this down again. So this is sigma 2s. Okay, sigma 2s. This is sigma star. That's 2. So 2, 4, 6, 8. Are we missing? I'm sorry, 4 here. That's not 2. Sorry. So this is going to be 4. 4 in the pi 2p, and let me go ahead and clean that up just a little bit. You can see that. Okay, so this is pi 2p bonding. Sorry, the board's not working too well. But anyway, you get it. Pi 2p bonding, there's 4 electrons. So we have 2, 4, 6, 10, 11. There are the 10 electrons. That's the electron configuration then for O2 plus. Okay. Bond order then. Let's go ahead and calculate for the bond order of this here. We have 2, 4, 6, 8 bonding electrons. We have 2, 3 non-bonding electrons. And we're going to divide that by 2. Okay. And so therefore we have then 5 halves, which is then going to be 2.5 for the bond order of O2 plus. Okay. All right. Go ahead and write that down. Hopefully you got that. Okay, let's go ahead and oops, sorry, let me go ahead and that really quickly. Okay. Okay, let's go ahead then and let's do O2 minus. Okay, so doing the same thing that we did earlier. Okay, O2 minus then, O2 with the negative. Okay, we have to account then for not 12, but for 13 electrons. Okay, so 13 electrons, let's go and write that in, filling in from the bottom. Again, we're going to ignore these atomic orbitals here. We're not, if you want to fill that out, you can, but for right now, just for the sake of keeping things a little bit more organized, so you can see this, and so that you focus in on filling in this table here, I'm going to leave those out. Okay, so starting, we're going to find the location for 13 electrons. Starting at the bottom, we have 1, 2, okay, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so there are the 13 electrons that that make up the O2 minus. So this is O2 minus here. Let's go ahead then and let's write out the electron configuration for O2 with the negative. So we have then sigma 2s, 2 electrons, sigma 2s star with 2 electrons. Okay. We have sigma 2p, okay, here with 2 electrons. Okay. We have then pi 2p with 4 electrons, and then pi 2p star with 3 electrons. And then there are our 13 electrons right there. Okay, bond order then, let's go ahead and calculate for this real quickly. We have 2, 4, 6, 8, 8 bonding. We have 2, 4, 5 anti-bonding. Okay, and we're going to take half of that. Okay, so the bond order here then ends up being 3/2, which is 1.5. Okay, so that's our bond order. This is the electron configuration for O2 minus, okay, O2 with the negative, okay. So which one has the strongest bond? So right now it looks like the strongest bond then is going to be O2 plus. Okay, so that would be the strongest bond because it has the largest bond order. Okay. All right. Good. Let's go ahead then and let's continue on. Hopefully you have that. If you have any questions, like I said, I didn't see anyone come by today. So if you have any questions, like I said, come on by and let me know. Oh, by the way, I had a request to open up and unlock the free response questions on the AP website. Please go there. Make sure you log on. Take a look at those questions to help you prepare for the AP exam. Okay. I had another question about what chapters the AP exam will cover. Real quick, then, let me get that for you. We have done all the chapters that will be covered on the exam. So basically, the AP exam will cover chapters 1 through 5, which we've done already. We'll skip chapter 6, which is thermal chemistry, 7, 8, 9, 7 through 11, which we're doing 7. We're finished through 9 right now. We'll do 10, hopefully starting Thursday. I think we can go through that fairly quickly. And then finally 11, 12, 13, 14, 15, 16. 17 is the thermal chemistry, which they will not cover, and also acid bases, which is 19 they will not cover. A little bit of chapter 22, which is the organic chemistry, which is the naming part. Make sure you remember that one. But outside of that, they're going to leave out the thermal chemistry, which is good news for you folks. Okay? All right, so if you have any other questions, please make sure you email me, and I'll respond to the email and or come by and see me. Okay? All right. Let me go ahead then and let's talk about what happens. Let me clear this up. Okay. With these molecules here, so I want you to take a look at number 8 here. I'm just going to go through these fairly quickly. We want to write down the electron configuration, the molecular order, and the bond orders, and write out the electron configurations for these here. In order to get the bond order, we need to figure out total number of electrons. And so let me go ahead and let's go through this really quickly together and draw this out and finish this up here. So let's go ahead and let's do dineon, and I'll leave diphosphorus for you to do, please. Okay, so let's take a look at dineon. Okay, dineon then we have to account for. Sorry, let me go ahead. Okay, so dineon. Remember, we're going to account for total of 16 electrons, 8 from each. Okay, so again, we're dealing with valence electrons. Okay, and so with that said, then if you remember the bond order, if you remember the order of the molecular orbitals, if you don't, just reference back to the couple previous slides. I'm just going to go ahead and write out the electron configuration here for dineon. And again, like I said, if you want to actually use the diagram to fill it out, go ahead and do so. But let's go ahead and write out the electron configuration here for dineon. It's going to be sigma 2s 2 sigma 2s star, okay, with 2. Next one in line is going to be a sigma 2p, and that's going to get 2. And then we're going to have then pi 2p, which is going to get filled with 4. Okay, and then we have then pi 2p anti star, which is going to have also 4. And then finally, we're going to have the sigma 2p star. That's going to have 2. And that accounts for your total 16. So it's got 2, 4, 6, 10, 14, 15, 16. So that is the electron configuration for dineon. And if you'll notice, then that order of filling will always be the same for every molecule. Okay, so you just got to make sure you remember then you have 2 types of filling. Two models that you can use here. The first one is the one where these 2 stay in order. This one, the second one, they just switch. And the way you'll know that is if you are given information about the magnetism of each one of these molecules, as well as photoelectron spectroscopy data. The bond energies and the bond lengths don't quite help you with determining which one of the molecular orbital models to use. the magnetism and the photoelectron spectroscopy should. Okay, so this here, obviously, if you take a look at this, then if we have all paired, it'll be all paired up, and so we expect this to be diamagnetic, which it would be diamagnetic. Okay, and it's diamagnetic because it's all paired up. Okay, so it's all paired up, and so we can go ahead and go about finding the bond order then. Okay. Right, so the bond order then is going to be the bonding. So we have 2, 4, 2, 4, 8, 2, 4, 8, 8 bonding. So we have 2, 6, 7, 8, 8 anti-bonding divided by 2. So the bond order here is going to be 0. And so in order to calculate the bond order, you need to get these, you got to get this electron configuration first in order for you to determine then which atoms are, which electrons are paired, which ones are unpaired. So real quick, do phosphorus, and then a diphosphorus, and then we'll do that together. Okay, so take about a couple minutes, about a minute or so to do diphosphorus, okay? And then we'll go over it together, okay? All right, let's go ahead and take a look at diphosphorus then. With diphosphorus, then we have to account for 10 total electrons, okay? 10 total electrons that we have to account for, okay? Now, with phosphorus, now we're in period 3. With phosphorus, we're in the period 3 elements. Now, it will not change how we approach this. The only difference now then is instead of blending together 2s orbitals and 2p orbitals, we're going to blend together the 3s orbitals and the 3p orbitals. And furthermore, you're going to recognize then that since phosphorus is right underneath nitrogen, we would expect then that phosphorus will order its orbitals in the same way that nitrogen orders its orbitals. Okay, so let's go ahead then and let's fill in the electron configuration for diphosphorus. And so just like with nitrogen, it's going to start out with the sigma, but this time it's going to be the sigma 3s, okay, because since we're blending together the 3s orbitals and 2 electrons go there, then we have then the sigma 3s star, okay, and we're going to have 2 electrons go there. Now with nitrogen, remember, the pi orbitals come next. The pi orbitals come next before the sigma orbitals for the p orbitals. Okay, so that means then what comes next then is going to be the pi 3p orbitals, and we're going to have 4 of those there. Okay, and so we have 2, 4, 2, 4, 8. We need 2 more electrons. Okay, and so those 2 electrons are going to fall into the sigma 3p bonding, and there's going to be 2 electrons there. So we got 2, 4, 8, 9, 10. There it is. So there are 10 electrons. Okay. All right, so that's the electron configuration for diphosphorus. The bond order then is going to be bonding electrons. We have 2, 4, 6, 8 minus the antibonding, which is going to be 2. We're going to divide that by a half. So the bond order here is going to be 3. Okay. So diphosphorus seems like it's a pretty good situation here where you have paired here, and the bond order is equal to 3. Okay, and so make sure you're able to get, and we find then that this we'd expect then that diphosphorus would also be diamagnetic because everything is paired up. Okay, so we have diamagnetic for both of these here, and so make sure you get that done. Okay, all right. So what we're going to do then is I'm going to quickly finish up. Let me just quickly, if I may, take a couple more minutes here. Okay. And let's clear this up. Let me just talk about then, up until this point, we've been doing homonuclear diatomic molecules. Homonuclear meaning then that the atoms are the same. You have two of the same types of atoms here, for example, dineon and diphosphorus. And we were studying how they could possibly bond together. Okay. Now, with that said, then most of the molecules that we deal with are not homonuclear; that they are instead atoms are made up of 2. The bond molecule is made up of 2 separate atoms. And so, how do we go about doing that? That is, how do we deal with what are called these heteronuclear diatomic molecules? Okay? So, the heteronuclear diatomic molecules, there's two different instances here that we have to account for. First of all, we want to talk about the neighboring atoms. That is, the atoms are fairly close to each other. Okay, so for example, here, let's take a look at what we have here is nitrogen monoxide, NO. Okay, so let's go ahead and take a look at this really quickly. So this is the electron configuration for nitrogen monoxide. Okay, so this is what we have. So these two atoms are right next to each other. And so if you notice then the way that they interact with each other is going to be very similar to the way that two nitrogens or two oxygens will interact with one another. The key difference though, and this is the problem that we have, nitrogen orders its electrons differently than oxygen does. And so what you'll notice here then is that the ordering that occurs here is the order that that nitrogen takes, and that is with the p2p orbitals taking being lower in energy than the sigma 2p orbital. Okay? Now, why this happens, again, you know, that's something for a later day. That's a discussion we can have later, and you'll come across this as you advance, if you advance in chemistry. But again, it's the significance of the blending of the 2p and the 2s orbitals here that accounts for that. So the electron configuration and the diagram, the energy distribution of nitrogen monoxides can be similar to that for dinitrogen rather than dioxin. Remember, with dioxin, you'd have these two flipped around. Okay. All right. Okay. And with that said, then afterwards, you just fill it out. So again, what you would do then is you have to count total number of valence electrons here, which would be 11 total electrons. If you count here, we start out at the bottom, 2, 4, 6, 8, 10, 11, and that's how you fill it in. The process by which we write out the electron configuration for heteronuclear diatomic molecules, very similar to what we would use for homonuclear diatomic molecules. Okay, so with that said, then I just want to quickly cover one last item so that tomorrow we can start talking about photoelectron spectroscopy, and that is what happens when I'm sorry, let me go back here. We had 2, 4, 6, 8, 10, 11. Okay, so I'm sorry. So it's going to take the oxygen electron configuration here. Okay, sorry about that. Okay. With that said, then the last thing I want to mention here is that with heteronuclear diatomic molecules in which the electrons are far away from one another, what happens in this the energy diagram is going to change quite a bit. Okay, so if you take a look at hydrogen fluoride here, okay, what you'll notice then is with the 1s, with the hydrogen atom here, the 1s orbital is going to be slightly higher in energy than the 2p orbitals from fluorine. Okay, so remember, with fluorine, then it has a 2p electron that it will use to bond together with the hydrogen atom here. The 2p orbitals here, so the energy differences here has to be accounted for. Bond does form, and so the sigma and the sigma star and the bonding and anti-bonding molecular orbitals will be slightly different in energy from, say, than if two fluorines or two hydrogens were bonded together. Okay, and so with that said, then that's all you really need to know for the heteronuclear molecules here. We rarely see this type of bonding questions on the AP exam, and I doubt if you'll see it this year at all. Okay, so actually I've read somewhere that you won't see this at all. So I would focus in on just trying to write out the electron configurations for the homonuclear diatomic molecules. Okay. All right, so with that said, then what we're going to do tomorrow then, and I would like you to take a look at this tonight, and that is that take a look at the last section of chapter 9, dealing with photoelectron spectroscopy. It doesn't do a very good job of covering it, so I'm going to give you a little bit more information about photoelectron spectroscopy, and then we're going to learn how to interpret it, and we're going to practice interpreting these photoelectron spectrographs. Okay, all right, so please take a look at it so we can go ahead and start with it tomorrow. Okay, all right, folks, have a good evening, and I will see you tomorrow.